Alright, I apologize for the technical issue I had at the end of the last video. I wanted to do one more example of Rolle's theorem though. Here, this time we're working with h of x equals x cubed minus 2x squared minus 8x on the closed interval -2 to +4. So remember the three conditions we need to meet. First of all, is this function continuous on the closed interval -2 to +4? Well, let's look at the type of function we're dealing with here. H of x is x cubed minus 2x squared minus 8x. This function, h of x, this is a polynomial. And polynomials are nice because they're continuous everywhere. So if it's continuous everywhere, it's certainly continuous on -2 to 4. So yes. Second condition, is it differentiable on the open interval -2 to +4. Last time we graphed it. This time, this is, I think, a little bit trickier to graph. I might suggest this time we find the derivative. I'm going to do that over here in red. H prime of x this time is x cubed minus 2x squared minus 8x. Nope, I forgot to take the derivative. I just copied down the original function, didn't I? Will be 3x squared minus 4x minus 8. And look at this function again. This function is also a polynomial, which polynomials are continuous everywhere. One part about continuity is that the function has to exist everywhere. And remember, that's really all differentiable says. It says that the derivative has to exist on this interval -2 to +4. So if it's continuous everywhere, or excuse me, if the derivative is continuous everywhere, it must also exist everywhere. So yes, it is differentiable on the open interval -2 to +4. Last part that we need to check here, is it the case that h of -2 equals h of 4? Because I need the endpoints to be equal in order for this theorem to hold. So here I need h of -2. Let's see, this will be -2 to the third power minus 2 times -2 squared minus 8 times -2. If we plug that in, we should end up with a y value of 0. I want to take h of 4 and plug that in as well. So 4 to the third power minus 2 times 4 squared minus 8 times 4. And, well, sure enough, we get a y value of 0. So our third condition is met. So yes, Rolle's theorem does apply here. So what that means is we have at least one point between -2 and +4 where h prime of x is equal to 0, where we have that horizontal tangent line. So now we need to go and find that point. And there's really not an elegant way to go about it. Rolle's theorem doesn't tell you how to find that point. It just says it exists. That's all it says. So I'm just going to take my derivative, 3x squared minus 4x minus 8, set it equal to 0, and solve for x. So I'm going to take, and let's do this in a different color. Let's do this in green here. I'm going to take 3x squared minus 4x minus 8, set this equal to 0, and solve. And as I look at this, 3x squared minus 4x minus 8, there's no common factors here. Let's see, can we factor this? 3 times -8, that would give me -24, and I'm just thinking out loud to myself here. Do I have two numbers which multiply to be -24 and add to be -4? We've got 6 and 4. That won't work. I don't think so. So this is not factorable, which means really the only way to go about this is to use a quadratic equation. I think that's the only way that we can solve this. Aside, I guess we could complete the square, but nobody really likes to complete the square, let's be honest. X equals opposite of b, 4 plus minus square root of b squared. This is -4 squared minus 4 times a is 3 times c is -8, all divided by 2a. This is 2 times 3. So here I've got 4 plus minus. Here this is square root of 16. 4 times 3 I've got negative 12. And then 12 times 8, let me just double check my arithmetic because I don't trust it, plus 96 all over 6. So let's see, 16 and 96 give 112. 4 plus minus radical 112 over 6. And let's see, can we reduce that? I believe we can. 112 is divisible by 16. So this is 4 plus minus square root 16 square root 7 all over 6. So this is 4 plus minus 4 radical 7 over 6. We can then simplify it to be 2 plus minus 2 radical 7 over 6. Whew. So I have my x values, 2 plus or minus 2 radical 7 over 6. But one thing I want to check is I want to make sure that both of them fall in that interval. I want to make sure that they both fall into that interval of -2 to 4. So let me just get a decimal approximation for each one, and let me do that in the upper left-hand corner here. I'm going to take 2 plus 2 radical 7 over 6 here, and let's evaluate that quickly. I got 2 plus 2 radical 7. Divide the result by 6. Here I have approximately 1.21. Yes, that falls in my interval of -2 to 4. So that means that this is one of the points that is guaranteed by Rolle's theorem. I'm going to check the other one as well, 2 minus 2 radical 7 over 6. This time 2 minus 2 radical 7. Divide the result by 6. This time I have, approximately -0.55. Well, yes, that's also in my interval of -2 to 4. So yes, this is also a point that is guaranteed by Rolle's theorem. So in this case, I have more than one point where I have that horizontal tangent line. It occurs at 2 plus 2 radical 7 over 6 and 2 minus 2 radical 7 over 6. The reason I wanted to check the decimal approximations again is just to make sure that they fell in our interval of -2 to +4. If we ended up with a value outside of that, let's say we ended up with 5.5. In that case, that value is not in my interval, which means it's not one of the values that's guaranteed by Rolle's theorem. We only want x values that fall in that interval. So we should double check if we have something like these ugly radicals. You may just want to get a decimal approximation very quickly and double check to make sure that that falls in your interval.